Okay, welcome back everybody to the Python tutorial seminar series. Today, Anderson will be covering Dask. This is a continuation from part 2. Oh, sorry, I should have corrected this. It should say part 2 on there. This session, like part 1, will also be recorded and published. Before the session, I need to review the code of conduct. By joining the Zoom call, you've agreed to adopt these values, engage in respectful communication, and if you do not, you'll be removed from the call. If you have any questions, members of the Xdev team will try to assist you in the chat, and just try to relax. We can get you up to speed in between sessions if that is insufficient for your technical difficulties. And some learning resources I'd like to point you to are Stack Overflow, the Dask documentation, and today's content, which is on GitHub, and it's been the same repository for these last 3 sessions. And with that, I will pass it on to Anderson.
Thank you, Julia. Let me share my screen. Okay, I presume you can see my screen. If not, let me know. Okay. Welcome everyone. So yeah, as Julia pointed out, so this is part 2. So we're going to build up on what we covered last time. So if you couldn't make it last time, I think you should still be okay following, but some of the things may not make sense, which in that case, then I invite you to go back to the recording and actually go through what we went through last time. So if you haven't done so already, so here's the repo. Some instructions on how to get the content locally. If you want to, and if you don't want to run things locally, you can just use Binder. So if you just go ahead and click the Launch Binder link, that should give you a live session that you can work with. All right. So let me. So a couple of things. Those who were not here last time, you may want to run this notebook. So 00-download data. So if you open that notebook and then just run it, that should download the data. And if you run this notebook last time, then you don't have to do this again. Just make sure that you're using the right environment. So in this case, I'm just going to use my local machine. So I cd into that directory, and then I activate my conda environment. And if you actually want to, you could also run that notebook from the command line. And the way you do that is if you go to the notebooks directory, and then where's the command? And then run this command. So this would actually run the notebook, but then from the command line. Just make sure you're in the XRA tutorial environment. So once you're done with that, then we can actually get started. Sorry about that. Yes, I need to do it. Okay. Yeah, so I'm launching Jupyter Lab. I don't know why it's taking too long. Okay. All right. So go to the notebooks directory, and then today we're going to cover these 3 notebooks. At least we tried to go through all 3. So the notebook you want to go to is 09-Dask array. Okay. So if you remember last time we covered a few basics as far as Dask is concerned. So we covered Dask delayed, which allows you to build custom parallel algorithms if you wanted to. So some of the topics we're going to cover today, in a way, may sound familiar if you've gone through the Dask delayed notebook. So things like lazy evaluation still holds for Dask arrays. The way that we're treating Dask delayed objects, we could also treat those. We could also treat Dask arrays as such, in that they kind of share the base, the core foundation. So Dask array. So if you're familiar with NumPy, you can think of a Dask array as basically it's a bunch of NumPy arrays. So usually, if you create a NumPy array, that NumPy array is on your local machine in the memory. But then what Dask array does, it then takes NumPy and then expands it so that it can actually have a collection of NumPy arrays on different machines that you can actually treat as a single array. So in this case, it's just distributed NumPy array. So in this picture here, you'll see that basically each one of these blocks corresponds to a chunk in Dask array, and each chunk is actually a NumPy array. So in this notebook, we're going to look at some of the features of Dask arrays, and we're going also to cover some of the API. And again, if you're familiar with NumPy, most of these things should look familiar. Okay, so the first thing that we do, as last time, we instantiate a local cluster. And then we're good to go. So, okay. So you may be wondering, how does Dask handle distributed arrays in this case? So under the hood, like I said, a Dask array is just like a bunch of NumPy arrays. And the way that Dask is able to run computation on that distributed array is basically by doing like small computations. So you can think of, let's say you wanted to compute a sum of an array, you could actually do that in small pieces. So you could take one chunk, compute the sum of that, do the same thing for all the other chunks, and then compute the sums of those sums up to the point when you basically are left with the final result. So this concept is called blocked algorithm. So you have an array that is chunked, and the primary operation can basically happen at the chunk level, and then you can accumulate the values as you go, and then you can compute more operation of those accumulated results. So yeah, so this is what this says here. So if you want to compute like a sum of 1 million elements, in this case, you have each chunk with 1,000 elements. You could actually just compute the sum of 1,000 elements, which leaves you with 1,000 sums, and then you can actually compute a sum of those 1,000 sums. So yeah. So let's actually see how this works in practice. So we're going to import Dask and then Dask array, and then NumPy and a few utilities here. So in this cell, we're going to create a NumPy array with this shape. So it's a 3D array of random values. So we can see the size of this array by just calling this function. So that's roughly 180 megabytes. So here's the same array, but then with Dask. So in this case, we're specifying the shape, but then in addition to the shape, we also have to specify the chunks. So as you can see, the way that we're specifying the chunks, so there's several ways to specify chunks. I won't cover I won't cover all of them. So what we're going to use in this case is what is called like a block shape. So in this case, I'm saying, if you remember, my shape is 600 by 200 by 200. And then I actually want to chunk it in shapes of 300 by 100 by 200. So each block has this shape. And then Dask will figure out how many chunks it needs to create. So if you to look at the Dask array, what you will see is that unlike NumPy, which if you try to print the array, it actually gives you the values, Dask is actually not giving you the values. And the reason for this is because it hasn't actually created that array. So what we have here is a representation of what we're going to get. So Dask knows that at some point it will have to create an array of this shape, and the chunks are going to be of this size. So it's also showing you, so this SVG image that kind of shows you the structure of that array. It will tell you the type of the array that it's going to create. In this case, a Dask array can hold other types of arrays. So in this case, it's going to hold an NumPy array. And it's telling us that we're going to have 4 chunks. So it hasn't actually created the array. And if you remember previously with Dask delayed, you could actually visualize the task graph, which will show you the computational graph that Dask is going to use to create this array. So if you run that, it may take a few seconds. So what this tells us is that, so we're going to have 4 chunks, as you can see, and Dask is basically calling numpy.random 4 times, and then it's concatenating these intermediate results into our single array. Okay, so that's basically how you would create a Dask array by hand. If people have questions, feel free to post them in the chat, or stop me if anything isn't clear. Okay, so we have our Dask array. So you may be wondering, then how do we manipulate it? So if you've used NumPy, you know that you can call these methods. Like for instance, if you wanted to compute the sum of the NumPy array, you just call the sum. The same thing holds true for Dask arrays, with only one exception. Again, because this is a Dask array, calling sum on it, it doesn't actually do any computation. It will just give us a lazy or a Dask array in return that we could then visualize and see actually what's going to happen. So you will see that basically calling sum, what Dask is actually doing under the hood is that it's actually computing the sum of each chunk, as you can see. And then once it has computed the sums, it then computes the sum of those sums. So it's aggregate those sums. And that's how you end up with a sum. Okay. So again, this is lazily evaluated. So we actually haven't done any computation. We just have a task graph build. Okay, so now once you're ready, you could then call compute. Let me first actually bring up a few things here. Progress stream. Okay. So now we can actually call compute, which should actually trigger the computation. So that's our sum of the total. And as you can see, again, if you remember from our last session, you can see, so each one of these blocks corresponds to, in this case, a single chunk or a single task in this case. So compute a random samples, the sum of the first chunk, and then actually, yeah, do this. You see that at some point, we actually transfer our partial results to some other worker that then computes the sum of those sums, and we get our final results. Okay. So, okay, let's go back here. Okay, so one thing to point out is that, so the number of tasks, so again, if you remember from our previous session, a task is basically, you can just think of like a function. So in this case, the number of chunks in a way dictates how many tasks we end up having. So in this case, I'm just using the same shape, but then I'm specifying a different chunk size. And what you will see is that instead of having 4 chunks, we now actually have so we have 12 chunks. And you'll see that the task graph in a way kind of gets more complex. So if you have more chunks, then you have to do more small computations, which in some cases it may introduce some overhead, but that's the idea. So this is it's a big deal. So usually the first thing to look into when things are slow is basically how you're chunking your data, because this in a way kind of dictates how much work Dask needs to do. So yeah. Okay, so this is basically the same computation as before, where we're computing the sum, but because of these smaller chunk sizes, we actually have more chunks, which means that we have to do more small computations. Okay, but then also another nice thing is that, as you can see, when the number of chunks change, we don't have to tell Dask anything in terms of how we should do the calculation. So in this case, Dask will basically adapt. So as you can see, it knows that, okay, compute the sum of each chunk, but then you can see that instead of just computing one, so if you go back here where we're just computing the sums and then we're aggregating those, you see that actually we're computing more partial results here. So we're computing the sums here, and then we're doing some partial sum here. We do it again here, again here, and then we do the aggregation here. And Dask knows what to do. So the nice thing about this is that basically it automatically basically design an algorithm appropriate for the operation. So you don't really have to do anything other than just chunk the data, and then Dask will figure out how to put these things together. So another thing is that as the nature of the computation changes, the task graph also changes. So in this case, so I'm taking my original array, and then I'm computing a dot product with its transpose, and I'm computing the mean along the first axis, and then I'm taking every other second element on the first axis, and I'm computing the standard deviation on the first axis. So what you get is something that looks like this. But then if you actually were to look at the task graph, it would look like this. So as you can see, it's more complex. So Dask will basically figure out what goes where and what communication patterns will get you the final result. So you can see that in some cases it's rechunking things and then it's doing some communication. But eventually you end up getting your final results. So yeah. So I have an example here that I'm not going to try out, but you can try this yourself. But one thing I wanted to showcase here is that we've been just working with 180 megabytes, which is probably not, it's not really big, it's really small. But this example here, let me just run that. I'm hoping at least this example will show you what Dask is capable of. So in this case, what we're doing, we're actually creating a much bigger array. So it's 23 gigabytes. If you're to try to create such an array with NumPy and you don't have that much memory, you probably just run into like a memory error. But with Dask, because it's doing smaller computations along the way, so it doesn't basically have to create this whole thing all at once. So it can basically focus on what it can fit in memory. So even though my computer has, I don't know, 16 gigs of memory, I can still go through 23 gigs. And let's see again, if you look at the task graph here, it's just going to be too big, I think. But you can try this at home and see. So the task graph is, I mean, it's too complex. If you look at it, it's, yeah, it's a mess. But again, whether it's 100 megabytes or 23 gigabytes, Dask will know what to do. So I'm not going to call compute on this because it may take some time. But when you get a chance, I invite you to try it out. Or if you want to, you could even just increase this instead of just, let's see, instead of 23 gigabytes, you could just increase this to, I don't know, 50 gigabytes by just increasing the shape of the array. So yeah, so that is Dask array. So there's a few things that I didn't show. For instance, if you use NumPy, you know that NumPy provides some utility functions for things like linear algebra. So some of those things are actually implemented in Dask, but not all of it, because some of the implementations, in a way, are really hard to do in a distributed fashion. So, so check the documentation; they'll tell you what works and what doesn't work. So there's a few also other things that Dask doesn't support. For instance, like if you're trying to mask, so if something you're trying to compute results into something that doesn't have the necessary information, in this case, if Dask cannot predict what the final outcome is going to be, so in this case, like the shape and things like that, it may not actually work. So one example is like masking one Dask array with another Boolean mask. So because if you're masking an array, but then that array is lazy, you don't know basically what values are coming out of that mask. And because of that, Dask cannot really predict, because it needs to know like the shape, the chunk sizes that are coming out, so that it knows what to do in case those end up being inputs to other tasks. So some of those things may not work. And then there's some other things that are just too difficult to do in parallel. Like, so one of those things like sorting. Like if you have an array and you want to sort it, and that array resides on one machine, then doing the sorting is very easy. But then if you now have a distributed array, how do you do the sorting? That's more complicated. So for some of these things, Dask actually doesn't implement this functionality. And then there's some other things that are just left out just because, so Dask is built by volunteers. So the things that are just left out just because no one has volunteered to work on them. So if there's anything that like, oh, this is useful for me, so yeah, please feel free to make some contributions if you have time. But yeah, so that is Dask array. And if you're interested, there's this screencast that goes into more details about Dask array. So I invite you to watch that at some point. And then I have some resources and references. Do you have any questions? Okay. Okay, it looks like most of the questions have been answered in the chat. Julia, if I missed any, let me know. Okay.
I think we're all caught up.
All right. Okay, so that was Dask array. We can actually just close this right here. Okay, now let's go to this notebook. So Dask and X-ray. Okay. So in most cases, you want you won't be using Dask array directly. So in this case, if you use Xarray, Xarray is actually using Dask arrays under the hood. What this notebook tries to do is just, in a way, introduce you to some of these functionalities. So, but understanding what the role Dask array does, in a way, kind of makes it easy when things break in Xarray. So we're going to look at, we're going to revisit Xarray objects, so data arrays and data sets. And one thing we're going to cover is that in some cases, Xarray objects behave like any other Dask collection. So if you remember, the Dask collections are things like Dask data frames, Dask arrays, and Dask blade. So the idea behind these objects being Dask collections are things that you would do on it, like a Dask array or a Dask blade object. You should be able to do those things on Xarray object directly. So you can, for instance, like visualize the task graph, or you can ask it to tell you some information about the underlying Dask data structures. So we're going to look at like a few operations that are built in that transparently use Dask. And then I'm not going to cover this because it's more advanced, but then there's some functionality that allows you to basically build custom functions that you can then map to chunks of Dask-backed Xarray objects. So this might just be a tutorial on its own in the future. Okay, so once again, we import a few things. So again, create an array. In this case, we're just creating an array of ones. That's the shape, and that's the chunk size. So we have 60 chunks. So we can actually tell Dask to give us the actual NumPy array by calling .compute. So as you can see, so this actually is a NumPy array in memory. So how do you get Dask arrays in Xarray? So if you've ever used Open Dataset and if you ever specified the chunks argument to that function, what you're actually getting is an Xarray dataset with Dask arrays in it. So in this case, let's look at one of the files that we've been working with for the last 3 sessions. So Open Dataset, and then we specify this chunks argument, and then we pass it as an empty dictionary. And what that does is that with an empty dictionary as chunks, Xarray is going to read so we're going to have one chunk. So so the entire file is going to end up in one chunk of a Dask array. So now if you look at the wrapper or the representation here, you'll see that if you're to go to the variable here and actually click on this database like icon, you see that it actually gives you information about the Dask array in this variable. So as you can see, we have one chunk. So the size of that chunk is basically the same as the shape of our array. And it hasn't actually read anything again. So this is just a representation of what we're going to get. So that's how you get a Dask array with Xarray if you're reading, let's say, an SCDF file. So this applies to other file formats too, such as GRIB or HDF. So in some cases, you may actually want to specify custom chunks. So in this case, I'm saying chunk. So this is a dictionary again, and the keys in this dictionary corresponds to dimensions. So I'm saying this is how I want to chunk time, latitude, and then longitude. So what do you see here? If you go back to the temperature variable, you see that. So those are our chunk sizes, which results into 2 chunks. and you can see the chunk sizes too. So basically now, when working with that NCAR file, we're actually going to be working with two chunks. So we can just, so Dask, so let's say in this case, if you had like a huge NCAR file and you probably don't have enough memory, you could basically just bring in memory only what you care about at that instant in time. And Dask should still be able to basically process that huge NCAR file. So if we just look at the variable itself, again, we get the same representation as before. We can look at the underlining chunks. Some of this may not make sense because this is just a tuple, so it's not as nice as the dictionary. So in some cases, you may have to basically consult the dimensions to know, okay, what does this correspond to? So this is our time dimension. So as you can see, we have that split into thing. Yeah. And so, yeah. So if you remember, I said that once you have an XArray object with Dask arrays in it, it becomes a Dask collection. So in this case, we can actually visualize the task graph. So if you call Dask.visualize, what you see is what XArray and Dask are going to do under the hood. So in this case, let me try to remember. So if you go back here, so you see that we have four variables. And as you can see in these four variables, we have Dask arrays in them. So those four variables corresponds to, so this is one variable, this is another variable, this is another variable, and this is another variable. These rectangles here, they correspond to the coordinates, I think. I could be wrong. But yeah, but the idea is you can see basically how Dask is going to map chunks to different operations. So, okay. So now let's actually go through some of the computation. So let's say you wanted to compute. So in this case, I want to compute the mean across latitude and longitude, and then I want to compute the dot product with the transpose of the original array. Again, because TOS is a Dask array, so this should be lazy. So it will just return a Dask, an XArray, their array with a Dask array in it. And so you can see the shape of that array and the chunk sizes. I can just do regular things. Like in this case, let's just select the first latitude. Again, since this is a Dask array, it's just going to give me a Dask array again. I can visualize this again, and then you'll see basically what's going on here. So it's more complex. So you can see it's opening the data, and then it's computing some mean, and then it's computing some transpose, and then it's doing some mean aggregation, and then so it's doing the dot product, and then it's so in this here, so the dot product is happening here, and then this is how you end up with the final result. So that's what the task graphs look like. So now we can actually call .compute. So that will just actually do the computation. And in this case, it will give us back an XArray data array with a NumPy array in it. Another way of doing this is instead of compute, you may see this in some documentation or some examples in the wild where people are using this load function. So it does the same thing as the dot compute, with only one difference, that the dot load is actually overriding. So basically, after you call after you call dot load, in this case, Z is just going to be a data array with NumPy arrays in it. So be careful when you try to use this, because this is just going to, if you have your data set distributed across a bunch of machines, what .compute and .load are doing is running the computation and actually sending the results to wherever this notebook is running. So in some of these cases, you may not have enough memory to hold on to that result. So calling .load.compute or .compute may be problematic, which in that case, what actually you want to try is there's a persist method. So what the persist does, it's the same thing as load and compute with one exception. So instead of computing the results and then sending them to wherever the notebook resides, it would actually it would basically cache the results in the worker's memory. So in this case, if let's say you're working on 10 separate machines, you now have a distributed memory across those 10 machines. Persist will just persist partial results on those workers. So it won't actually send anything, which means that if you ever need these results, you can get them quickly because you don't have to go through them again, because they're just somewhere on some machine, but you're not sending everything to one machine. Okay. So that was one example. We were just using open dataset. So one very crucial utility provided by XRA is this function called OpenMF dataset. So you may have seen it. In case you haven't, OpenMF dataset under the hood is using open dataset to open multiple files. So you give it a list of files, and then it will basically open those files, create datasets, and then concatenate them into a single dataset. And by default, by default, you can actually tell XRA to use Dask to read those multiple files. If you do that and you have Dask installed, it will actually use Dask under the hood to call open dataset multiple times to create those individual datasets and then do the concatenation. So if you recall from our example in our previous session, so we had this example, we're going through a list of files, and so each file here is a single ensemble member. And what we wanted to do was to compute anomaly for each of the ensemble members. So we're basically looping through the files, and then for each file, so we're using Dask delayed, which allows us to do these things lazily. So we call delayed on open dataset, which gives us a delayed object, which we can use that delayed object to actually access some of the attributes on this object. So I can just group by and then compute the anomaly here. And then at the end, I'm then combining this. Remember, this is a dictionary. So where the keys correspond to the ensemble members, and the values corresponds to the anomalies for each one of the ensemble members. So now I'm just concatenating them. So if we run this, so this is how you do it manually. So it's just looping through and then constructing this task graph, and then at the end, it's computing everything. But then with OpenMF dataset, you basically don't have to do this because you can actually pass that list of files to OpenMF dataset, and you can tell it the concatenation dimension. So in this case, this dimension doesn't exist, which means that we're actually creating it. And then we can tell it how to do the combination. And then it's the parallel equals to true that tells it to use Dask under the hood. And then what specify, so this is this option allows us to control how some of these dimensions are updated on the final result. So in this case, we don't want to say take time and then have time be a 2D array where we have ensemble member as a new dimension. So I'm just specifying we're only interested in this particular variable. And then I specify the chunks. The chunks here, they don't correspond to the final dataset. They correspond to what goes to each file. So this is being passed to open dataset. So this is how I want to chunk each file. So if I run that, see that, so there's some activity here, and then what you get back is basically a dataset with one additional coordinate dimension, ensemble member, and you see that basically now my temperature variable now has, it's 4D, so ensemble member, time, lat, and mode, but then everything else is still intact. Okay, so that is Open MF dataset. So if you ever find yourself in a position where you have like a bunch of files that you want to concatenate into a single dataset, so that's the function to use. And for some more complex cases, you may basically want to use Open Dataset and then do the concatenation yourself. So yeah, so there might be some instances where this doesn't work out of the box for you, which in that case, then you can use Open Dataset, still use chunks to do things lazily, and then figure out how to concatenate the data sets that you're getting. So, because basically that's what Open MF dataset is doing, and they're just using Open Dataset to read each one of these files and then concatenate them. Okay, so now that we have this one dataset, we can just do our regular computation as if we're just looping through those files. So in this case, what I'm doing is, again, extract the TOS variable, group by time.month, and then remove the climatology from the original input. And what that gives us is, again, it's a 4D array of anomalies. And also has a Dask array in it. It will tell you some information about the shape, the chunk sizes. So in some of these cases, you may notice that the chunk size that we have here are different from the ones that we specified previously. That's because of the nature of the operations that are happening here. So there's nothing that says that whatever you started with as chunk shapes is what Dask keeps using. So in this case, I'm interested in just plotting those anomalies, and the plotting by default would invoke the computation. So if you call .plot on something that has a Dask array in it, under the hood, Xdev would actually call .compute for you, because there's no way you can visualize something lazily. So yeah, so that's OpenMF dataset. So I have an example here where I say, okay, as you can see, so this is what you would do if you didn't have OpenMF dataset. So you write all this code, which then becomes just this code with OpenMF dataset. So yeah. So that is, so basically at this point, once you have this dataset, you can just treat it like any other X-array dataset. So you can just do whatever you would do on an X-array object. So that's why I don't really go into more details about. So at this point, basically, Dask isn't that special in that you can just do whatever operations you would do with a Dask, with an X-array dataset backed by NumPy. But then recall those exceptions or those warnings that I gave in the previous notebook about how some of these things may not work due to the fact that they're not just implemented in Dask. Okay, so yeah, so that's Dask and X-array. Do we have any questions? Okay. Well, looks like Deepak and Julia took care of the questions. Okay. Yeah, so Andrew asks, so basically adding parallel equals to true to an MF dataset read will invoke Dask. Yes, so that's what, otherwise, I think the default behavior is that internally Xdev would actually loop through those files. So it has basically a code path that is just doing stuff serially. So if you have like 100 files, you're basically looping through that list of 100 files one by one. Whereas with parallel equals to true, you can actually just open all of them at once So yeah. Okay, so that is Dask and Xarray. Let's see. Okay. So again, I have a few resources and references here. People are interested. And now let's actually look at this last notebook, which, okay, hopefully, let's see how much time we have. Okay, 10 minutes, okay. Okay, so, well, it's perfectly fine if you don't get to cover everything here. But what this notebook tries to address is actually something that we've been using, but we haven't really explained why and how to use it. So remember, we're creating this cluster where, so if you go back here, we created this cluster here, right? But then we didn't really go into the details of what's going on here. So that's what this notebook tries to address. Okay, so I'll try to go through this as quick as possible. So in the previous examples, we're using the distributed scheduler. And Dask provides a bunch of other schedulers. So there's a threaded scheduler, which basically the way you can think about it is that you have this like a bunch of threads. And then there's a processes scheduler, which is basically backed by like a bunch of processes. And then you could also, there's a single threaded scheduler, and this is usually good for debugging. So what the single threaded scheduler does, it will basically turn off any distributed logic, and then it will actually just do this as if you're just running this on like a single thread in a single process. And that becomes useful if you, let's say you want to debug things. And the nice thing is, so the threaded and the processes and the single threaded schedulers, they don't require any setup. So you can just tell Dask at any point in time, this is the schedule I want you to use for this particular computation. So here's what I mean by that. Recall how we do .compute. So what under the hood Dask is doing, it's trying to figure out which scheduler is active. By default, if you use the distributed scheduler, that's what Dask is going. If you instantiate the scheduler, the distributed scheduler in your session, that's what Dask is going to use. But you could actually tell it that you want to use a different scheduler for a block of code that is part of your computation, and this is how you would do it. So you would import Dask, and then you would then use this context manager. I don't know if this was actually covered in the introductory Python tutorial, but this with statement in Python, in a way, tells Python he's a context manager, which means that use these settings, and then once you exit out of this context, basically go back to whatever was active before. So in this case, we're saying, we don't care what scheduler was active before. We just want to use the processes scheduler and to compute this. And what this will do, because the processes scheduler doesn't require any setup, basically Dask will just launch a few processes in the background, and then we'll just do the computation. And then we'll then discard those processes once it's done. Or in some of these cases, you may want to set it globally. So instead of just using the context manager, you can just do dask.config set and then tell it what scheduler to use. So we can try some of these schedulers. So for instance, you'll see that in this notebook, I haven't actually created any Dask cluster. But then if I run this, you see that I actually end up with a Dask array in it. That's because by default, I think I could be wrong, but I think by default, if you don't have a scheduler setup, it will actually use the threaded scheduler. One disadvantage is that you cannot use the dashboard. So the dashboard is only available for the distributed scheduler. So you cannot use the dashboard for processes or threaded schedulers. There's some custom built diagnostics for those schedulers, but you won't get rich information as you would if you're using the distributed scheduler. So I can do regular stuff here. So compute the anomaly again. And now let's actually look at something here. So what I'm doing here, I'm just looping through this list of schedulers, and at any point in time, I'm telling Dask what scheduler to use. So I'm basically computing the same thing 3 times, and each time I'm using a different scheduler. And I just want to see how they compare. So in this case, we're doing the threaded scheduler, the processes, and then this is the serial version. And we'll print out some runtime as it gets done. So we can see that the threaded scheduler took 0.6 seconds. I think process is still running. Should be done, I don't know when, in a few seconds maybe. And then lastly, we're just going to use this single thread scheduler, which basically is a single thread in one process. So in the meantime, we can basically start asking ourselves, like basically, like how much speed up would you expect? Like in this case, we're using like a bunch of threads, and then in this case, we're using like a bunch of processes, and then in this case, we only have like one thread. So this is actually not even parallel. And what you're going to see is that the processes is actually way slower than the threaded scheduler, even for the synchronous one. So you may be wondering, oh, I would expect that if I just throw like a bunch of processes to this problem, then it should be faster. It depends on the nature of the computation here. So one thing to keep in mind is if you have a bunch of processes, each process is holding on its own memory, which means that the only way you can get the processes to talk to each other is basically by actually communicating, which in a way, usually communication is one of the bottlenecks. Whereas with a threaded scheduler, you basically have a bunch of threads in the same process, and those threads actually share the memory. So if they wanted to communicate, they don't need to send each other anything. They can just point each other to different location in that pool of memory. And then you have the synchronous. So this is serial. So as you can see, this one is slower than the threaded, and this is also again due to the nature of computation we're doing here, which is so we're using NumPy, which usually if you're using NumPy, NumPy code is usually faster if you have multiple threads due to how it's built. And then another thing to keep in mind when it comes to processes is that there's an overhead associated with launching processes. So as compared to threads where you basically have one process, the cost to launching multiple threads as compared to launching multiple processes is smaller. So yeah, and also this also kind of depends on how many CPUs you have on your machine and things like that. And then this kind of goes into some of the details about exactly why the threaded scheduler is fine in some cases and why sometimes it's not. So if you ever heard of this thing called the GIL, so the Python Global Interpreter Lock, which says that basically at any point, if you have like a bunch of threads in a single process, only one thread can actually take control of the Python interpreter, which means that if there's any, basically if the code itself isn't releasing the lock, basically you're having to wait so that the next thread can actually do the computation, which in this case, NumPy is actually doing computation at the C level, which in that case, it doesn't actually hold on to this GIL thing. So if you want to go into the details of what the GIL means, then here's a blog post for you. Okay, let's see. Okay. Okay, 1 minute, and then I'll take questions. So this section goes through the distributed scheduler, and one thing to keep in mind is when you're talking about the distributed scheduler, you're talking about a couple of things. One, there's the cluster. So you can think of the cluster as just a collection of the scheduler itself and the workers, and then you need a client to be able to talk to the scheduler, because these two things, so the client and the cluster could actually reside on two different machines. As an example, let's say if you have access to like a supercomputer like Cheyenne, in some cases, you could basically have the client on your local machine talking to a cluster that is on Cheyenne or Casper. And that's why basically you need this client object so that you can actually talk to the scheduler, depending on wherever it's located. So usually this is what local cluster is doing under the hood. So we create a cluster, which gives us this piece, so the scheduler and the workers, and then we create the client, which we then connect to the cluster. So the reason why I introduce this is this works well on a single machine. So we've been just using this on our laptops. But then let's say you go to Cheyenne or you go to the cloud, it's just a matter of changing how you're creating the cluster. So for instance, on HPC systems, there's this project called Dask Job Queue, which will actually allow you to create a Dask PBS cluster, for instance, or a Slurm cluster that knows how to talk to PBS or Slurm. And then you can take that cluster that you're getting back, and then you can actually connect it to your own client. In the cloud, there's also a bunch of other ways. So there's Kubernetes, Dask Kubernetes, and then there's a bunch of these other things. So depending on what environment you work in, my recommendation is to go and look at some of these projects. So if you work on a supercomputer, you may actually want to look at Dask Job Queue. And what you're going to change is basically how you're instantiating the clusters. Instead of local cluster, you do, let's say, PBS cluster on a system with PBS, or you do Slurm cluster on a system with Slurm, and then you just create the client exactly the same way. And then if you switch back to your laptop, you just create a local cluster. So there's a bunch of these. Unfortunately, we're running out of time. So so that's at least something that I thought, or I think is useful to know. So now that you know how to create a cluster, so look at what system you're using, and then figure out which one of these projects makes sense. And if you run into problems or you're not sure which one to use, feel free to email us, and then we'll at least figure out what resources to point you to. So yeah, so unfortunately, that's where I'm going to stop because we've run out of time. And then I can take a few questions.
Anderson, could you briefly talk about scaling studies in terms of how big is your data before Dask becomes worth it, and how to pick an optimal chunk size, balancing having with your number of workers? Like what does some of the scaling suggest?
Oh man, okay. Okay, that's a hard question, because I think it depends on the nature of the computation. So if you remember when I started the previous session, I had this tweet that basically even Dask people will tell you that if you can avoid Dask, please do. And the reason for that is once you get into Dask, you are introducing more complexity to, so now you used to work on one machine, now you have 10 machines. Then there's a bunch of other things that now start slowing down your computation. So it could be the file system, if you're reading data off of disk, it could be the communication, basically how do those machines talk to each other. So I think one thing that at least I found to be useful is the dashboard, because the dashboard in a way tells you some information about what's going on in the cluster. So for instance, you might be able to tell basically what's actually slowing down your computation. So in this case, one thing that could create some problems is, let's say you chunk along a dimension, let's say time, but maybe actually the nature of the computation requires that you know everything along that time axis. So and then if you think about it, if I only have a small chunk of that time axis, I have to communicate to get everything along that time axis before I can actually do anything useful. So in that case, the way that's going to show up on the dashboard is, if you're looking at the progress, it's going to show up as red. So if you like a bunch of reds on the dashboard, that's usually a sign that there's so much communication going on. And that may have to do with chunks. In some cases, that may have to do with the nature of the way that algorithm is written, which in that case, there's no one size fits all solution. So usually it's basically like a few days of digging deep and finding out exactly what's going on, or just asking other people. So my recommendation is, before you, let's say, create like a distributed cluster, let's say, even on a bigger machine, let's say Cheyenne or Casper, before you even start creating a cluster with 10 machines, maybe try with getting like a single, so submit one job with enough resources, and then just use the local cluster on that single machine. And then once you are comfortable that things are working as you would expect, then you can then go into scaling up. Because if you start scaling to 20 machines before you even know that things are working properly, then when things break, debugging becomes too complex. So in this case, if you can start small, I would say start small and then only throw that problem to a bigger cluster once you're confident that things work. Because usually the debugging process in this case involves just trimming down your problem to a small size and then trying to figure out what's going on and then going back to the full size problem. So if you're working, I don't know, terabyte of data, you probably don't want to do debugging on a terabyte of data. So unfortunately, I don't have a good solution or a good answer. So my recommendation is just start small and only go big when you're at least confident that things work on a small scale.
Thanks,
Otherwise, if you're interested in chunking schemes and things like that, there's some papers that have been written. I can send those to Julia when she sends the recording information. She can share those with you if you're interested in going deep into exactly what's going on and figuring out some of the best practices for the chunking and things like that.
That'd be great.
Any other question? Let's see. Okay. Okay, so there's a question from Dan who mentions this other project called Intake ESM, which, so Intake ESM hides OpenMF dataset. Yeah, I think that might be an interesting topic to cover. Yeah. Let's see. Do you have any other questions?
Okay, Anderson, thank you so much for your time and your wisdom. Thank you everyone who attended. We'll be continuing the seminar series. Look for a link soon to submit some of your ideas.
All right.
And we'll see you on August 11th.
Right. Thank you,
Oh,
Julia.
today's August 11th. I mean the 25th. Bye.
Right. Thanks.